the quality of the ground, but you have also a radiated power modification because of the losses in the ground, which happen in a less such a big
a lesser extent to the
for the horizontal. So the vertical are very sensitive to the ground quality, which is not the case of the horizontal antennas. Okay, so we have to speak about the quarter wave because according to the size of the antenna, the thing are changing. First question is what we call the near field efficiency. We will see later the far field, but you have two different problems: the near field and the far field, which means the near ground and the far ground. The efficiency is according to the antenna. It's very easy to understand. You have the radiating impedance of your antenna, which most of the case is 36 ohms. Okay, and you have to divide it by, because actually an antenna, you have the antenna, that's your antenna, and you have RL, loss resistance, in series with it. So if your antenna is considered as a first resistance of 36 ohms, you have the power is between that really transmitting resistance and that warming resistance. So the efficiency is 36 divided by the total resistance. In most cases, I don't know why I come back. So the air losses is coming from two things: the antenna wire, including a coil, if you have a coil in the antenna, and the ground. About the wire, Frances, hein, tu pourrais essayer de vous.
Non, c'est
Ah, ok, d'accord. There is some formula to calculate the wire, but I made the calculation for you. On 160 meter, the antenna, shortened antenna is 20 meter long. It gives you a 2 ohms of resistance. If you, for example, use a piece of coax with 11 millimeter shield, you divide it by 10. That means that 2 ohms compared to what we will see is neglected. Negligible. That one is not easy for me.
But that formula is including skin effect, is that right? Or?
Yes, yes. That's the whole. Yes, I will diameter.
Yeah, surtout nous envoyer le PowerPoint pour qu'on l'ait. Puis,
yeah, but that's a copy of RRL antenna book, so
okay.
you read it in the book.
Okay.
But you know, I'm not supposed to diffuse.
C'est vrai,
there is a copyright on it. Joe, I can use it because I'm setting it. I'm saying from where is the source, but you have to buy the book to have the book, so it's not that expensive. It's $40, something like that. So this is just an example. This is not an absolute Bible thing because the opinions are different. But for quarter wave vertical antennas, you can the loose resistance, the resistance of the ground can be found on this table. So you can say that that's the length of the radials, and that's the curves with the number of radials. So if we can, the average guy who have 16 radials, you can see that the losses are of course getting lower when the radials are getting longer. But what you can see interesting on that, in that if you use few radials, it's useless to have too long radials. Because even if you get longer radials, the losses are the same. But if you increase the number of radials, in this case, it's interesting to have longer radials. You see? And by that, we will see that again later, but you start to see that there is an optimal length for the radials according to the number of radials.
Okay.
And by that, you can imagine that there is an optimal length and the number of radials according to the quantity of wire you want to invest in your antenna.
What about, but this is not, this is only the resistive, the radial system could have a reactive
Yes.
component if it's short, right? Or is it always purely resistive?
No, because we are speaking about the
Assuming you need tuning on
the
it.
imaginary component is only
Gets
a
tuned out.
question of matching,
Right, okay.
not a question of losses.
understand.
We are talking about losses there.
Okay.
So what you can see that is another value from this is from ARRL and that from 1,4UN book. That one is the resistance of the radial system for a quarter wave on 160 and 80 meters. It's because that's of course that value change with the frequency because we will see later why. So I prefer that one. I think it's more close to the reality because I find that one very optimistic. That one shows you that if you are for example on 160 meter, it's difficult to have 0.15 is already 25 meter length. So it's difficult to do more for radials practically. And you can see that with 15 radials or 13 radials, that does not change much. So if I double the number of radial, I'm wasting my time and my money.
Yeah.
Okay?
Change the
But
length.
of course, if I am able to have such a long radial that 40% of the wavelength, then doubling the number of radial is very efficient. Okay, you see the difference?
Multiplying the cost too.
So the guy who has two radials and make them half wavelengths is an idiot. No, but that's or someone ignoring the radio. Okay, so you have to find your way there, but that's the reality. Now we will take an example of that. If I have my antenna 36 ohms, because that's the value, and I have 15 radials, okay, sorry, I have 15 radials this side, I can take 15 ohms. And if I add to that 2 ohms for the wire, as we see, that is about 17. 17 is nearly the half of 46. So we have 70%. Well, about 70% of no less than that.
66.
2/3, 66%. Let's say 65% of efficiency.
67.5.
Well, okay.
What? I'm having trouble understanding why is the loss in the radial for what could be an equivalent or larger wire so much more significant than the loss in the vertical element?
Because the loss in the vertical element is only because the resistance of the wire, the piece of wire,
Yeah.
which we saw is not very high.
But isn't this because of the resistance in the wire? Well, how else is it
No,
dissipating?
no. It's because of the height of the antenna and the fact that most of the current is at the base of the antenna.
Oh,
So-
is this loss into the ground, basically?
yes. That's
So it's
only
not-
the loss into the
So
ground.
it's not
Yes.
being dissipated in
You know, it's
the
equivalent.
copper. It's
No, he added the 2 ohms.
No, I did the two
That's the
ones.
copper. So that resistance is RL on your diagram.
But you are supposed to have a quarter wave vertical, which is pretty high for the low bands. I'm going further, but
Gilles, juste fait.
yes,
La résistance que tu as dessinée à droite,
oui,
sa valeur is the RL.
yes, it's a
Radi-
loose resistance.
Okay,
Okay, and the loose resistance is the sum of the ground,
the ground loss resistance.
the radial resistance plus
plus the copper.
Plus the copper.
plus, if needed, a coil resistance,
Plus the
which is around 2 or 3 ohms with a good Q. So, it's just an example to show you a value, what we are losing. So, now come back to the number of radials. That's the question everybody is questioning. Before starting that, there is a third parameter, which is the diameter of the radials. Often the people, which wire will I use? Okay, so it's very easy to understand the diameter. The diameter of the radials if you have a vertical wire which is some number 14, okay, you just need to have the fact that the sum of the radial diameters must be equivalent to 14. Yes.
Okay,
How come
so
I've never seen this
Who
anywhere?
has
Yeah.
said you have number
How come
14
I've
on
never
every
seen this
radius?
anywhere?
That's
so
crazy.
so number 14 radials.
J'ai toujours.
No,
Because
that's
the
not what I
curve-
said. But
The
I
diameter.
think
Okay.
if you put 16 radials, you can put number 24.
Okay.
Then the only limit is the mechanical resistance of the radials. So where do you put them? If you put them on an EV traffic place, you will have to have a wide one. But if you put them in a place where nobody pass, you can put number 40, number 24. And for myself, I bought 10,000 feet, a roll of 10,000 feet of number 24 with plastic insulation.
Magnet wire? No.
No, plastic insulation.
For
I
your
bought
radial system.
the big coil.
Okay,
You know,
radial, oui.
and with that I make my radials because as I put a minimum of 16, it's far, and it's the more cost effective.
They don't degrade over time, like 24
No.
seems like.
No, because they
They're
are protected
insulated.
by the isolation.
The rings of your plastic.
Yes. So the idea is that the mechanical resistance comes from the plastic, and the conductivity, the number 24, is enough.
Did you buy stranded or solid?
Solid. Imagine stranded 24.
24, yeah.
That's going to be very thin. Okay, so now let's go on the length of the radials, because it's some work. Even if you buy some 24, which is not much expensive, it's some work to put them on the ground.
Actually,
So it's much time to invest. So, as I told you, for a given quantity of wire, an optimal exists. Okay? So, out of this optimal, you're wasting time and money. That's obvious. Because when you have to double the number of radial, I don't know if you have ever run the radials on the ground, but I tell you, when you have put 16 of them, you will not want to double that number. Especially when you have 4 antennas in phase. So, you are looking for the minimum of work, not only minimum of cost. Then, there are some optimal. There are different point of view according to the books. You can refer, but just for your ID, you say that they are giving the ID according to that. So length of each radial according to so that's the IRL point of view. As I told you, I think it's very optimistic. That's another point of view. I prefer that one. I think that more effective. 0.15 for 16, and that's practical. Okay, now another point of view is the length of the radial versus the number of the radial versus the quality of the ground. This is for, as you can see, an average ground. Okay, you see that with the 10 meter length radials, here you have the number of radials, and here you have the gain of the antenna. They don't say which gain it is the maximum gain. I expect it's the maximum gain, which is not very interesting, but it's a way to compare. As I told you, you can see that with only 10 meter length radials, on 80 meter, you cannot improve anything beyond 8 radials. You can see that increasing the length of the radials for a given number of radials don't give any gain. Okay? The gain is obtained by lengthening the radial and the number of radials at the same time. Now, if we go to a poor ground, you see that here, between, if we get this case, the difference between that one, here you are 1.25 dB, and here you have -1 dB. So the difference between two is a 2 dB affair. If you go to a very poor ground, you can see that -4, 1, it becomes to be a 5 dB affair. So the worse is the ground, the more important are the radials. Okay? In this case, you can see that with the 10-meter radials, you have some improvements with increasing the number of radials still because you're on a poor ground. So it's like if you are a big resistive ground and you have to put a big shield to prevent your field to come into the ground. That's the idea. Okay? That's a very good ground, which you can be expected nearly salt water. In this case, you see that you don't need much radials, neither very long radials. Okay? Then, as I told you, the worse the ground, the more important are the radials. Now, about elevated radials, we are already seen by the simulation that they are supposed to have the same efficiency that the perfect set of radials, but as I told you, there are the problem of the 8 by itself is not very practical. This perfect symmetry is needed, what is nearly impossible, not constant by the time, because the radial effective length is varying with the weather, with many parameters. Of course, they are more visible and cumbersome. And what the conclusion is that you need a minimum of 8 radials. When I say the minimum, you would prefer 15 or 16 radials. So you are coming back to the same problem as the radial of the growth, but you can have a gain of 1 or 2 dBs. So now I will speak about, because you always, I do not spend much time on the conductivity of the ground, and I have to spend time on that because it's a very important thing with the vertical antennas. We have 2 constants to measure the ground. Actually, it's what? It's the ohmic resistance of the ground. Yeah, you take an ohm meter and you measure actually the resistance of the ground.
Is there a length?
That's the conductivity. The conductivity is inverse of the resistivity. I don't like this unit, but like that.
It used to be moles.
Yes.
M.O.
So it's mole. Yes, you're right. It's a reverse of ohm.
But Siemens,
Okay. So that's the Siemens per meter. And the dielectric constant is just like for a capacitor. So it's a way to measure the capacitance of actually the dielectric constant is the ability to multiply the capacitor. You know, when you take two metal plates, you have a capacitor between them. And in the air, you have a capacitor. When you put some material inside, that capacitor will change. The higher the dielectric constant, the higher this capacitor will be. Okay? And you can multiply that by until 15, for if you use of mica, of whatever. So the 2 constants are defining the ground. And you can consider your ground like you know the line with resistor and capacitor, delay line or filter. So that's a way to modelize the ground as it should be something like that. Whatever. What happens is that we usually use those constants. You can find those values everywhere, including in the simulating software, and you can see some values varying from 18 to 3. You can see that what we usually use is that 13 and 006 for average, but 005. And you have perhaps ever seen that map. That's the map for the connectivity in the USA. Of course, we have not the Quebec, but we can imagine that the Quebec, that Montreal is in the number 4 value. Okay, so it's 0.004 instead of 0.005. But actually, what the story don't say is that the map has been done for broadcast. And broadcast is low frequencies. It's under 1.5 megahertz. So the reality is not that. You know, what happens is that if you look to the RMM antenna book, they give you an example of the evolution of the conductivity with the frequency. And you see that it changed much with the frequency. So your 0.005 should be valid for half megahertz or 1 megahertz, but surely not at 15 megahertz or 30 megahertz. So that don't give the real story. The same for the permittivity. You see, it's varying with the frequency.
Permittivity goes up,
Yes. A last thing.
down with frequency.
A last thing is that the very important thing is I think that the figure very interesting because it gives you the deep the ability of the waves to go inside the ground. That's the depth. It's not the real depth. It's the depth of attenuation. That means it's the depth where the wave is attenuated by 1 on E because it's an exponential.
Okay.
So I think it's around 0.7%. No, I don't remember exactly, but that's about that. That means that those values that you can see is the depth where the wave is attenuated by 37%. You still are 60%. So if you go on 15 megahertz, you and on an average ground, okay, you are 4 meters deep. So imagine at 4 meters you still have 60% of signal. That means that for your vertical antenna, your signal is going about 10 or 20 meters deep in the underground.
So all those resistances add.
Exactly.
And the deeper
So
those.
all the resistance of that is underneath your antenna, and that gives another idea of the effective depth of your effective height of your antenna over a virtual real ground. Yes.
So if you're installing radios, can you improve your ground situation by
Exactly.
adding some
Yes.
gravel or some material
Yes,
around?
yes, because putting the radials, you are creating a screen, preventing the wave coming underneath. It's like a shield. Yeah, you protect your wave for having them to be same in the sky, not warming the ground. That's the idea. And why there is an optimal between the length and the number of radials is because it's when you are going far, the distance is going more important. It's why at some length it's ridiculous to have very long radials and few radials because when you are far, there is a big distance there. So it's why you have to add more radials. It's to have a lower distance here. Here it's okay. And it's what you can have few radials. When you are short radials, you better have few because the distance is okay.
And what happens when you're in an ideal situation, you have all your radios going out at 360 degrees all around the base of your radio antenna? An ideal situation is your radials are spread out 360 degrees around the base of your antenna.
Yes.
But what happens if you don't have enough room?
What happens is that in that direction you will have some losses.
Okay.
That's what happens. Because you can make some simulation, you will see that actually where you have the radials, you have the usual, the correct radiating gain of the antenna. When you are missing radials in that direction, you will
have less.
You will miss some signal. So that's very interesting, and you see that in the water, that's not the same case.
Can you
In the seawater, actually the waves are not penetrating, and that's the reason why there is less losses on the seawater.
What happens if we put a pond underneath, a bassin d'eau under a vertical? Will it help?
But that should be good, but it must be some seawater, salt water.
Okay.
Because fresh water is not very especially good.
Okay.
It's good, but not especially good.
So if we make our own.
Yes, but in this case, I think it's easier to put some net. The net for the farmer net.
Okay.
or whatever, it will be less costly than putting some salt water at.
Okay.
Your wife might prefer a pond.
Yes.
That was actually.
Well, you can
question
grow
I had
saltwater
is,
plants,
instead
saltwater
of
fish,
having
yeah.
like
Seasonal though.
120 radios,
So it's freshwater.
can you simply just put like a grillage?
Climate.
Yes, you can.
Ok, puis tu le connectes, il va
Yes,
tout
yes,
se connecter ensemble, tu le connectes tout à la base.
Exactly, you can put that. Yes.
Quite a
Does
mesh,
ice
a
behave
screen.
like water?
Yeah, it'd be
Sorry?
a ground plane,
Does
right? Not
ice
radio,
behave
ground
like
plane.
water?
Yeah.
In terms of RF?
No, I think no. I think the ice is
maybe not, but-
nearly transparent.
Transparent.
Transparent to the way.
Mais pas l'eau.
It doesn't
No,
water
yes,
doesn't-
it works as a dielectric.
Just like water, just like fresh water. Because ice is, well, this is frozen
I don't
salt
even
water.
know. I
Frozen
don't-
salt water probably,
No,
So,
I did not remark any change in the impedance of my
Frozen salt
antenna
water?
with snow or ice. Yes, what happens is that when you have ice around the dipole, for example, the frequency is lowering. The resonance frequency
dielectric,
because
the
of the
dielectric
dielectric,
loading.
yes. But actually, it not give you any losses. That's important.
C'est le dielectrique
And
qui
for
change.
example, you know that there was an expedition at St. Peter Island, which is in the Arctic, and there was on a ice glacier. And,
Glacier.
A glacier.
Glacier.
A glacier, a glacier.
A glacier, on a glacier. And so they put the antenna very low. Because actually the ice doesn't cool, so they were like if they were very high. You see? So that's an interesting point. So another thing with that is that the actual wavelength in the source is shortened by far. If you take the average ground, you see on the 15 megahertz, 1, 2, 3, 4, average, like, hey, the wavelength is 2 meter instead of 20 meter divided by 10. So that's have an influence on the. There is a very big influence on. Of course, it's underground, okay, but there is for the military. It's very interesting because they can hide antennas underground not to be seen by radars. You see, and they can still transmit, even if there are losses. There are big amplifiers, so they are able to hide the antenna underground.
well, of course, if they really, if they're able to get out, it still should be possible to see it by radar if you're looking down.
Yes, but
But
yes.
it's not sticking up in the air.
Yes, and they are shorter too, because for 20 meter you just need a 2 meter length dipole.
That used to be good with planes and satellites.
Because of the dielectric
It's
concept.
You know, you go on 15 megahertz. So I was
see
present. You know, here is 15 megahertz. Okay. I'm sorry. Yes, I say 2 meter. No. It's actually 7 meter. If 15 that's 20. 15 should be there. That's the average. We are somewhere there. So 1, 2, 3, 4, 14 meter. So 20 meters outside becomes 40 meters underground. You are shortening your antenna. I said
Because of the dielectric.
yes, but if the ground is better, the antenna is getting shorter and shorter.
Okay.
So that's why the radials on the ground, if you want to put quarter wave radials, you don't need to put a full quarter wave. You can have shorter radials. So now, a very important thing is shortened verticals, because if you go on the low bands, you will need some shortened verticals. I'm sorry that I cannot zoom more on that, but that's again something that you can look at the same time on the RL antenna book and the ON4UN book, is the length in degrees of the antenna versus the impedance. Actually, it's not the impedance, it's the radiating resistance of the antenna.
Okay.
Well, what means the useful part of the resistance of the antenna for transmission. What you can see on those curves, it's that, so I just explained, 90 degree means a quarter wave. It's not always obvious, and 45 degrees means an eighth wave, okay? So imagine you have you are 160 meter, and you are just able to put an antenna 20 meter high, vertical antenna. So in this case, 160 is the quad wave is 40 meter, then 20 meter high is 45 degrees. The same thing if you are on 80 meters, a 10 meter high antenna, which is good, is 45 degrees. Then you can see that when you base load your antenna, that is the curve for the base load antenna, so you put a coil at the base of your antenna, so you will have an efficiency, you will have a radiating value of 7 ohms. Okay?
Not so much.
7 ohms. So remember, you have not 26 or 36 plus air loss. This time you have 7 ohms on 7 ohms plus 17 ohms in our example. In this case, it's not the same thing. You have 7 out of 24. So that means 1/3. So you are nearly 30% this time.
Instead
So
of 60 something.
2/3 of your power is getting in the ground.
Better than I thought, though.
Yes,
I thought
But-
it was getting out with about 5%
perhaps.
on 20 meters.
Perhaps. And then, now if you are top loading your antenna, you don't put a coil, but you put just a wire at the top of your antenna, but that's the coil, okay? Now, if you are doing that, or whatever, the important thing is that the total length of wire. Because when you are top loading an antenna, actually what you are doing, you are putting a capacitor at the top. You see, you have the choice between putting a coil at the base or a capacitor at the top. The capacitor is between the top and the ground. And you can count that a piece of wire is 6 picofarad per meter. So if you need, for example, 50